This talk will present our work titled Dual-Stream Multiple Instance Learning Network for whole slide image classification with self-supervised contrastive learning. I'm the presenter, Bing Li, from the University of Wisconsin and Madison. Histopathology is the process of extracting and visualizing human tissue sections for disease diagnosis. Modern slide scanners are now capable of converting glass slide-mounted samples into high-resolution whole slide images at multiple magnifications for examination and analysis. Tumor detection is one of the major topics in digital histopathology. The challenges come from that whole slide images have vastly high resolutions and usually lack localized annotations. Developing methods for tumor detection in whole slide images relying on only slide-level labels has been a long-standing goal. Patch extraction is often necessary for processing whole slide images due to the big image dimensions. However, for an unannotated tumor slide, which of the extracted patches are positive is unknown. In this setting, the classifier is given a set of images but only a global label that indicates the existence of positive patches, and it is trained to predict the label of the image set and differentiate positive patches. The problem is known as multiple instance learning, where the patches are referred as instances and the set is referred as a bag. We built a solution for whole slide image classification following the formulation of multiple instance learning, where the model is trained on a large number of unannotated slides. Our work builds on the existing study of attention-based multiple instance learning. We design and integrate a non-local network to our model and use contrastive learning for pre-training the embedded network. Our work is also motivated by the recent success of weakly supervised learning methods for tumor detection in whole slide images. Our method first extracts patches from whole slide images at multiple magnifications. For each magnification, an embedded network is trained on the patches using self-supervised contrastive learning. The patches are then projected into embeddings and form feature pyramids, which are then used for our multiple instance learning network. Our multiple instance learning network consists of a two-branch architecture. The first branch uses max pooling on the scores produced by a linear classification head operating on the instances, which determines the critical instance with the highest score. The second branch learns a back representation, which is a weighted sum of the instances, where the weights are determined by the distance between the instances to the critical instance. The two branches together form a masked non-local block where the attentions are computed only between the critical instance to all instances. Using the similarity to the critical instance as regularization, our method can therefore lead to better decision boundary than conventional operators such as max pooling. Training the multiple instance learning network and the embedding network end-to-end could be difficult for the prohibitive memory requirement of big bags and the existence of unbalanced bags where a positive bag only contains a small number of positive instances. Therefore, we propose to use self-supervised contrastive learning to pre-train the embedded network. This allows good representations to be learned from large number of unlabeled patches and reduces the memory requirement for big bags by pre-computing the embeddings of the patches. It is common to consider features for multiple magnifications for whole slide image analysis because of the large image dimensions. We propose to construct feature pyramid using embeddings for multiple magnifications, where the embeddings from lower magnifications are duplicated and concatenated to the embeddings of the higher magnification that belong to the same lower magnification patch. The resulted embeddings will then have same parts if they are spatially close to each other. This mechanism thus applies a spatial constraint on the attention scores, which are computed based on similarity measurements and also incorporate information from multiscale. We first evaluate our method on two whole slide image datasets that are publicly available, namely Chameleon-16 and TCGA lung cancer datasets. The Chameleon-16 dataset consists of 400 whole slide images and was built for breast cancer detection. The TCGA lung cancer dataset contains 1,053 slides with two subtypes of lung cancer. We compare our method to several recent models. The classification area under the curve and the localization-free response receiver operating characteristic show that our method outperforms previous state-of-the-art methods with an average of 2%. We further visualize the attention maps generated by the models. Our model performs better in delineating tumor regions in whole slide images. To show the effect of using self-supervised learning features, we compare the features learned using different pre-trained methods. The result shows that self-supervised learning leads to superior features compared to ImageNet features, and even better than features learned by end-to-end training using max pooling. At last, we test our model on several multiple instance learning benchmark datasets. Our model shows a clear-cut improvement on the classification accuracy over the recent models and demonstrates a state-of-the-art performance. In conclusion, we proposed a novel multiple instance learning network for tumor detection in whole slide images. We use self-supervised contrastive learning to learn features for the multiple instance learning network. We implement a multi-scale attention mechanism for whole slide images. The additional benchmark result on standard datasets further demonstrate the superior performance of our network on general multiple instance learning problems. For more details, please check out our poster and GitHub repository. Thanks for watching.